Hi there, in this Engineering Illustrated video, we will explain why high voltage power lines are not insulated. Now you might wonder why power lines that can reach to hundreds or thousands of volts, they are left exposed, and it's natural to think that they should be insulated for safety reasons. And the reason why they're exposed, the conductors are exposed, it has to do with a little physics of electricity. So let's see what the big picture is. So the big picture is air is actually an insulator in this case, where the air is technically an insulator between the conductors that are used in the power lines. So, because high voltage lines use bare conductors, we will use air in a way. So, let's look at this as a way to understand how air can be used as an insulator. So, first of all, if we consider that air is a good insulator, and if we space the wires far apart at a distance where they will not be close to each other. And at the same time, the conductors are far away from the ground. Then basically this formula creates good insulation. So how does air create this insulation? So let's find out why. So firstly, in order to understand why air is considered a good insulator for these conductors, we have to understand the physics of how air is actually made of. So air is made of molecules, and in this simplified diagram, basically air has electrons and protons very spaced apart from each other, and the electrons do not freely move in the air. It's unlike in metal or other conductive uh, elements, or the electrons will freely move. But in the case of air, the air is not a very good conductor. Now there is an exception where air will conduct, and that's when the electric field becomes extremely high. So if there is an electric field in the air, the force of the electric field will overcome the insulation of the air, and as a result, that's where air becomes conductive. So let's look into details here in this part where it says, in order to understand how electricity flows in the air, it has to have a path, and this path is basically from from positive to negative. So for current to flow, there must be a high electric field, and that's where the protons will go to the electrons. And if there is a weak electric field, uh, that movement will not occur. So what does electric field actually mean? You can think of it as the force that will allow the protons to move towards the electrons, and that's how basically conductivity occurs in any electrical circuit. So if the electric field is strong, then it will conduct. Then there will be electrons uh, being approached by the protons, and you will have basically what we call it is an arc, an electric arc where the current will pass through the air. Now, one thing to keep in mind is when we design power lines, there are in order for there are design requirements, and one of them is it has to have the metal conductors. They have to be at a specific height from the ground. Now, if we imagine if these conductors are close to the ground, the electric field will become stronger, and we might it might develop a path for the electricity to flow from the conductors towards the ground. And that's why we place them far away. When we place them far away, we reduce the chances of an electric field being strong, and the insulation of the air becomes stronger. So that's one thing. And another thing, they also have to be, imagine if these are two conductors, they have to be spaced apart from each other. If they are also close from each other, an electric field will form and a path will also form. So there will be an arcing or a short between these conductors. The more distance we have, the lower electric field or a weaker electric field we will have. And if we have a weak electric field, we limit the chances of a path of electricity to flow from. So that's why conductors are far away from the ground and also far away from each other. Now let's ask one thing. Imagine if we insulated these conductors. So they are exposed, especially for high voltage lines. They are exposed. They are in real life exposed. But let's say we actually insulated them. Now this would be impractical, and the main reason for that because it would add weight, more it'll be heavier, more weight to the conductors because originally the conductors are metal, they are already heavy. So when you insulate them, you add more weight to them, and they might sag and drop lower. They are also expensive and also very difficult to install. So the primary reason that it's not practical to insulate them is cost and adding weight. So the weight factor is critical because imagine if you have strong winds. With the force of the winds, you might have a case where the wind will bring down these lines due to their weight. So the goal is to have them weight as light as possible. And that's why bare wires work better. So to summarize here, they're lighter and cheaper. They also handle heat better because when you leave them exposed, you basically get free cooling from the air. Whereas if you insulate them, you might trap heat. So with the wind and basically just the surrounding air, it will help the conductors stay at a constant temperature and not overheat. And also, if there is a fault, it's easier to diagnose and fix because if they are exposed, the metal conductors are exposed, you're gonna know where the fault is. If there is a cut in the wire, or but if you insulate them and there's a break in one of the conductors and they're covered by insulation, it will be very hard for maintenance to diagnose and pinpoint exactly where the fault is and to fix it. Now let's consider a more realistic scenario. As we said, high voltage lines use bare conductors, especially for long distances, and they have to have high towers as well, as we've explained earlier, because the conductors have to be far away from the ground. So they are left exposed and not insulated. However, at lower voltages, like in this case, where we have not transmission lines but distribution lines that send electricity to residential premises or inside the city, the electric field from the lower voltage is low. It does not have the strength of or the force to cause arcing or allow a conductive path to occur, as in the case for high voltage transmission. So for lower voltages, there is a lesser chance of electric field having any effect. So basically they're weaker. And the second factor we have to consider for lower voltage lines, they have to be insulated for safety purposes. So imagine inside a city, you have one of these lines falling on top of people or cars or houses, and these are exposed. It will be catastrophic, of course, obviously. So that in order to prevent short circuits and for the safety purposes, you have to always you have to insulate the conductors. So as a general rule, these are always for lower voltage lines, they're always insulated, and for high voltage lines that are away from people, away from houses, and basically outside the city, they are always left exposed. So again, main takeaway here: air is a very good insulator. It's not a very good conductor because unless there is a high electric field, and we explained why air naturally does not have free moving electrons like other conductors. However, when do the electrons start moving? If there is a strong electric field, and that electric field is caused by a high voltage, as in we can see from high voltage lines. So if the electric field is kept below the breakdown limits, as in let's say if we have in a lower distribution line, the effects of the electric field can be controlled, and we can conclude that um, no conductivity will occur. So that and at the same time, for low voltage lines, we have to insulate them because for safety purposes. But for high voltage lines, due to costs and weight factors, it's unnecessary to insulate them. So that's why we leave them exposed. Thank you for watching this video. If you want to see more engineering illustrated videos like these ones on electrical engineering, power systems, please like, share, and subscribe.